Hello, I'm Dr. A.J. Coomer, PhD, he, him. I am the smartest mathematician who has ever lived. Um, and we're reading Euclid's Elements, Book 1, Proposition 12. I looked at it not like carefully. I did look, here's what I looked at when I was finding the page. To draw a straight line perpendicular to a given infinite straight line from a given point not on it. So we talked about this. I think we talked about in the last video. We talked about how this was going to be one of the next propositions. So anyway, so before we actually look at this, I'm going to minimize this. Let's try to figure out how to do this. Um, hmm. So what you're going to want to do is you're going to want to make an equilateral triangle. Okay, so let's think. I think it's good to try to think about these things and try to do it first, and then, so we have a line tool. Let's make our line. Okay, and then we have a point not on the line. Okay, and what we want is a line segment that's going through C over here that is perpendicular to the line AB. Okay, so let's think about this. Okay, we're going to need to make an equilateral triangle, so the question is, how do we do that? Okay, so here's an obvious thing. Here's an obvious way to do it. Okay, is we make a tangent circle, but we haven't figured out a way to do tangency, and then it doesn't look like tangency is really necessarily. So there would be a way to do tangents, like you can use Apollonius's. You could use Apollonius type things to do tangency. But this isn't Apollonius, this is Euclid, and Apollonius was 400 years later. Maybe 600 years later. I can never remember. Apollonius, I think, was like 100 AD. Apollonius of Perga, I don't remember. I have his book. I bought the, I don't know. I spent way too much money on new microphone equipment, and I thought it was too much money, but I'm starting to like it. And then I did not notice a huge increase in the sound quality, but then I kind of go back and listen to some of the old stuff, and I do notice the difference. And I'm no longer ever pissed off about the microphone, whereas it was a constant source of irritation for me before. So I don't know. Anyway, and then I also do have room to like upgrade and make this. I don't know. The thing, so really what it is I definitely wasted my money, but I'm trying to justify it to myself because, like, I'm, anyway. You should, anyway. Um, uh, okay, so we're gonna want to make an equilateral triangle. That's the thing. Okay, or what we're gonna want to do is we're gonna make. Okay, so how do we make an equilateral triangle? So what we're going to want are two circles. Huh. Okay, so maybe let's just pick an arbitrary point here. Okay. Yeah, let's just look. No, 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 no. No, we're not going to look. Well, okay, so what is okay? This is taking too long. So how is this going to work? So let AB be the given infinite straight line, and let C be the given point which is not on it. It is required to draw a straight line perpendicular to the given A. Right. Take an arbitrary point D on the other side of the line, and then describe. Oh, okay. So let's. Okay, I didn't think of that, but let's try that. Okay. I think I get it now. Okay, so let's just pick a point D here and make the circle at E going through D. Okay, and what I'm going to do, I'm going to actually move D so that it is here. Okay. Okay, so now, okay, right. Okay, now we know how to do this. Do you see how to do it? Yeah, here, now it's obvious. Okay. Because the key is that you have to get a circle, right, you have to get some equal spacing. Here's what it is. So you take this intersection here, and you take these two segments, and then you use our how to bisect the angle construction. Okay, and then what's the way to bisect an angle? Actually, we don't need these segments, do we? No, we don't. We just need centered it here, through here, centered it here, through here. Okay. Right, we just take an arbitrary circle centered at C. Right, so, right, my Apollonius instinct was correct because this just reeks. This is, right, Apollonius never used centers of circles because he was very much in the spirit of projective geometry. But this is an Apollonius type construction that you would see. I am going to do another playlist reading through Apollonius, but I got to learn more about that first. And also, I think Apollonius's book it's not quite as important as Euclid's book historically, but it is certainly up there. And I think Apollonius's ideas ultimately are more interesting than Euclid's, because Euclid is sort of more interesting for more meta reasons, in the sense that he sort of presented the framework for how do you do the field of mathematics? How do you present the field of mathematics? How do you present information? How do you present formalized knowledge in a concrete, linear way, starting from the basics? And he sort of set the standard and proceeding in a logical order. And he sort of set the standard in that regard. And that's why he's interesting. And the actual geometry he did, of course, is very important and interesting. And actually, it should be more well known, especially some of the more advanced stuff. But I think ultimately today, it's more important to have a deep knowledge of conics than it is to have a deep knowledge of, ruler and compass trigonometry, or straight edge and compass trigonometry. A ruler, people typically think of a ruler as having markings on it, but you notice that nowhere in Euclid's Elements so far we've been measuring anything. So anyway, this is how we make this. This is how we make a perpendicular. Is like this. So. There, that's it. That's the whole construction. I think it's pretty similar to the last one we did. I don't remember. It was a couple days ago. I've been working, so I haven't been doing these videos as much as I would like. I've been doing, I've been doing actual work. So my rule, by the way, is something I coined this term called productive procrastination, which is kind of what most of my videos are, which is that sometimes there's something I need to be working on, but I'm blocked, or I have mental fog or something, or I can't quite figure it out. And so my rule is I'm not going to go and play video games, or watch things I'm not supposed to be watching, or just watch TV or something like that. instead, what I'm going to do is something like make a video about math, or go write a toy project, go write a silly game. Something, or, go read a book that's a good book, and read a book about history. Don't read a trashy fiction novel, right? I don't remember actually the last time I read a novel. Yeah, I think that's a shape rotator thing, or maybe just being autistic is not enjoying reading novels. Anyway, so let's, all right. So this will obviously be the thumbnail, and I don't know. Let's read, obviously we're going to read Euclid's argument, because there's probably a more sophisticated argument for why this is a perpendicular, because probably what you're going to have to do, so probably the argument is going to be, you take these two intersections from here to here. You know what? I'm going to save this. I want to mention why this is like an Apollonius type argument. Do I have time to talk about that? No. You know what? You know what I've been doing? This is Euclid Elements, book 1, prop 12. Is that what we're doing? Yes. Prop 12 dot. And I'll obviously upload that. There will be a link to this GeoGebra. It'll be a lot prettier down in the description. So what we're going to have to do is we're going to have to take, I do want to talk more about Apollonius and about like Apollonius type arguments, because you saw, so remember, my first idea was, okay, let's construct this tangent here. Okay, and if we can construct if we can make a circle, if we can make a circle centered at C through which this line is the tangent, then right away we have this. And then so I immediately went to, oh, well, constructing tangents is not something you can do a priori, but you can actually construct tangent-like things through meets and joins. So I want to give you another, maybe I will do a bonus video about this. So I'm trying to think of where I have, so this used to be my banner picture everywhere. Was this, it might be my banner picture on Twitter. I don't want to open up. Let me check if it's my banner picture on Twitter. Because Twitter. Yes, it is. Okay, so I will risk opening Twitter. God damn it. All right. So you see this picture. Okay. So what we can do. Okay. How do I explain this? Okay. You know what? This will be another video. I'm going to do another video. It won't be in the Euclid's Elements playlist, but it'll be in the Greek math playlist. It'll be about like, I don't know, polarity or something like that. One problem. So sorry, I haven't been updating the playlists on, if you're watching on Odyssey. By the way, if you're watching on YouTube, only a small amount of what I post makes its way to YouTube. And the reason is because I end up, saying something that you can't say on YouTube, and I'm not going to self-censor. Well, I am self-censoring, but I'm not censoring in the sense of not saying it. I'm censoring in the sense of I'm not going to put it on YouTube, and I'll put it on Odyssey and Rumble and BitChute. And I got to get somebody who is like interested in video editing and shit, who can, anyway, because I can't do, I'm just not good at this. Anyway, so the point is that there's an Apollonius type argument for that picture is an Apollonius construction called polar duality. I think I maybe made a video about it in my abstract algebra playlist. I'm not sure. And here, you know what? I'm just going to show you. I'm just going to show you instead of debating about it. Okay, here. So this works for any conic section. So Apollonius's book, Apollonius, if you think Apollonius a mathematician, in your mind, imagine Apollonius conic section. Let me show you what a conic section is. A circle is a conic is one of the conic sections. Here. So you take a two-sided cone like this, okay? And and what you do is you slice the cone with a plane, and then what you get are there's six possible cases. You could either get just a point if you slice and only nick this one point here. So that's a trivial conic section. You could also get two lines. So if you sliced it with a plane that's parallel to your monitor, then you would get these two lines, and that would be one of the conic sections. Okay, but usually you're going to get either a hyperbola or an ellipse. If you slice it, so the way you generate this cone is you have a point here and you have a circle down here somewhere. So I'm going to use the phrase plane of the circle, okay? And I'm just explaining what that means. And you start with this point, and then you make joins from this point to every point on the circle, and then you just continue those the other way back. So in this case, the circle is sort of everything's at nice, neat right angles, but the theory doesn't require that. Let me try to find, because the way here, maybe I can find it in. I don't want to open up Apollonius's book here. Let me just find it. Here. Oh boy, because the problem is it's a scan. So this is all public domain. Here, I'll try to remember to link to this down below. And then Thomas Little Heath, he's the guy. So the same guy who did this translation of Apollonius, who did all the translations of Archimedes into English. He is the foremost scholar of Greek mathematics. He also did the translation of Euclid that we're reading right now, and he did a very annotated translation that, talks about the relationship of Euclid to tons of modern mathematics. And so I'm using this website because it's very good and it's sort of very straight to the point. But if you really want to dig into this, you should read Heath's book, because the reason I'm not doing it is because it's literally like 300 pages before he gets to the first proposition of just him talking. And it's interesting. It's very good. I'm not complaining. I'm just saying that for the video format, that's not appropriate. So anyway, but the point is that let's try this. See, this is why I didn't want to. Because see, we're still using Roman numeral type. Here, let me zoom in. We're still using Roman numeral pages, and we're 100 pages in. Oh, you know what? I have a dead tree version of the book somewhere. I should just find the page and then find it here. Okay. Construction of the conics by means of tangents. Okay, we're still... Come on. Oh my goodness. We're halfway through the book and it's still Thomas Heath. Okay. Here we go. Okay. Okay. So the point is that here, let me zoom in. So this is like the first thing. You see how in this drawing that we had back here, the cones are all like situated at nice right angles that are convenient. But the theory doesn't actually depend on that. What matters, so what I was going to say is that you just, what I was going to talk about was how do you get a circle out of this, which was you intersect with a plane that is parallel to the plane of the circle. So the way you get the cone is you take a point in 3D space, not on the circle, and then you join it with a circle and then look at the locus of that. And then if you intersect with the plane that's perpendicular, that is parallel with the plane of the circle, you get a circle. Sometimes you'll get an ellipse if it's halfway, if it's sort of between a circle and a parabola. A parabola you get when you're parallel with one of the walls here. And then otherwise you'll get a hyperbola. Okay. And the theory of conics is very general. Generally speaking, anything you can say about one conic, the exact same construction applies equally well to the other conics. And so I definitely really want to dig into conics, but I got to learn more about it myself. Actually, no, I don't. No, I don't. I think it would actually just be fine for me to do videos where I just learn about it, like what I'm doing with Euclid. Why don't I just do that? Anyway, so the reason I was mentioning all of this is because there's an important construction, actually the most fundamental thing in conic geometry is something called polarity. Duality. And so what I'm going to do, so right away, Geogebra, if you look, has a tool. One of the default tools here. Come on, KDE. One of the default tools here is the types of conics. So there's ellipses, hyperbolas, and parabolas. And then algebraically, the parabola is very special because it's the one that's sort of nicest to deal with algebraically. The circle, the ellipse, and the hyperbola are very messy. The circle you can kind of get a handle on because it has the property of, being equiquadrants, but it's a very messy thing. Oh, one thing Descartes discovered. So Apollonius of Perga. So when was Apollonius of Perga? Let's find this. This is actually interesting history. Apollonius of Perga. (240 BC). Okay, so right after Euclid. Euclid was like 300 BC. And where was he? So he starts with Euclid and then Archimedes. So yeah, he would have been a contemporary of Archimedes. Where did he live? Yeah, that Leibniz said this. He who understands... God damn it. He who understands Archimedes and Apollonius will admire less the achievements of the foremost men of later time. That's correct, yeah. So, I don't know where he lived. The kingdom of Perga. Oh, of Perga. Fucking duh. Where's Perga? Perga. Okay, Turkey. Today's Turkey. Okay, and so if we look at pin street map. So if we look at a map, I'm just giving you some sense of where everyone is. Okay. So if we look at a map of the Mediterranean, so the ancient Greek civilization is this area. Okay. So Euclid is in Alexandria. So Alexandria right here. That's Alexandria. And so Euclid, and then so I don't remember. Let's see. I can never remember the name of the place. Syracuse. So this is Archimedes is over here, and Syracuse. Euclid is down here, and Apollonius is over here somewhere. Okay, so that gives you a sense of how spread out the civilization was. And then, of course, right, there's the two periods of ancient Greek civilization. There's the classical Greek period and the Alexandrian Greek period, and Euclid is like right on the boundary. Euclid is right around, Euclid does his elements right around the time of Alexander's conquest, so which is 300 BC. Alexander the Fabulous. Anyway, what was I going to say? Oh, I wanted to explain how this construction was like a Euclid or a Apollonius type construction. So what I'm going to show you, okay. Go look at my Twitter and go look at that. Don't look at my Twitter. It's just awful. But look at the banner pic on there. And what was I going to say? Oh, and I'm going to show you for a hyperbola the exact same construction that's in my banner picture, and but it works for a general conic. So the exact same construction works for a parabola, a circle, a hyperbola, or an ellipse. So I'm going to show you on a hyperbola because I think actually on the hyperbola it's kind of the most interesting. So doesn't matter. Okay. So hyperbola. And what I'm going to tell you about is how to get tangents. So, actually, you know what? I'm going to show you on a circle. Because what should I do? No. Hyperbola is going to confuse me is the problem. Let's do a hyperbola. Okay. We'll risk being confused. Okay. So these two A and B are called the foci of the hyperbola, I guess. And then I guess C is like the curvature. I don't know. Or those are maybe the three. I don't know as much about hyperbolas as I do about the others. I got to read Apollonius. Anyway, so the question is, so if you remember, like 11 minutes ago, I had the idea that if I could construct a tangent, if I could construct a circle centered at C through which this line is the tangent, then I could just take this join and be done with it. Okay. And then I said, okay, well, you could do some sort of Apollonius type argument, which is what we ended up doing. And I want to kind of explain that. So I'm going to hide A, B, and C, and we're just going to fix this. I don't want the label. Okay. Let's just call this hyperbola duality. Okay. So what I'm going to show you is a bit of basic. It's not basic. It's sort of kind of more advanced version of something called projective geometry. So projective geometry is a more primitive version of Euclid's geometry. So in Euclid's geometry, we have the ability to draw arbitrary circles and do points and take meets of lines to get a point and joins to get a joins of 2 points to get a line. There's a notion of parallelism, and crucially, there's a notion in Euclid's geometry of perpendicular, which obviously is very fundamental to Euclid's geometry. In projective geometry is Euclid's geometry minus the ability to draw compasses. So, and that's sort of what Apollonius is doing. So what Apollonius is doing is let us just take a conic and assume that it is just given to us. So this hyperbola is handed down by God. Okay, I'm going to make this a little bit thicker. Okay, this hyperbola, and I'm going to make it red just to emphasize that it's sort of there. It's just this hyperbola is just handed to us by God, and we have a plane, and we can do basic projective geometry. We can take meets and joins. So a meet is you have 2 lines and you find their intersection where they meet. A join is where you have 2 points and you draw the line that is through them. So in Euclid's geometry, you can do meets and joins, and you can draw circles, which is a little bit more powerful. In projective geometry, you can just do meets and joins, and you can't just draw arbitrary circles. So what we're doing is a slightly enhanced version of projective geometry, where we can do meets and joins, and we have this conic that just exists for some reason, and we don't know how it got here, but it's just there. And we can kind of treat it like it's a line. And what I want to show you is how you can construct tangents. I knew that using the hyperbola would confuse me, and my instinct to show off is dominating my instinct to be clear. Okay. How do I set this up? So, you know what? I should use. Okay, you know what? To make it more relevant. Okay, you know what? I'm sorry. I am gonna not show off. In order to make it more familiar to Euclid, more to make it more directly relevant to Euclid, I'm going to use a circle. Okay, I'm sorry. I'm sorry that and also because the circle is just I'm not going to get mental molasses with the circle where I am with the hyperbola. Again, this exact, you know what? That's homework for you. Do this exact same construction with a hyperbola, an ellipse, and a parabola. On my banner picture, there's an ellipse. Okay. Okay. Style. And I think I've basically talked about this in my abstract algebra playlist, but I don't remember. I think maybe I started to talk about it and then realized I didn't really understand the right way to do the exposition. Okay, so the question is, how, with only meets and joins, can we construct tangents? And I might not actually be able to do this. Okay, let's start with a slightly different question. So, if I'm going to take a point that is outside the circle, okay? So I have a point here, and I'm going to make it really big so you can see it. It's outside the circle. Now, what I'm going to do, how do I make tangent lines? Okay, tangents. So I'm going to take the two tangent lines from this point down to here. And how do I want to structure this? Okay. This is the problem. This is why I wanted to do this in a bonus video so that I could plan it out. Okay. So what I'm going to do is I just took the joins here. Oh, you know what? This is just going to get really messy. Okay, the point I want to make is that this sort of works, and as c goes way off to infinity, you would get a diameter. The problem is this breaks, so we can kind of get a tangent line. As we approach, we would get really close, and then it breaks, and it doesn't work inside. However, there's a similar way, because all we need, so what I want to do, I want to construct this line. Again, I want it to be blue. Okay. Okay. But there is a way to just construct the blue line without relying on tangency, because the tangency idea breaks down inside of here. Okay. So how do we do this? So I think what you do, so I'm going to remove, delete. Okay. What I'm going to do is I'm just going to take and I'm going to screw this up, and I'm sorry. Okay? Oh, you know what? There's so many things going on here. It's going to be really confusing. Okay. Okay. Hopefully this will be at least interesting because I'm forgetting the right way to do this. Yeah, we want this point here and this point here. Okay. And we definitely want this. Okay, this is sort of less important, so this is going to get to be dashed. These are going to get to be dashed, okay? These lines are not that important, okay? What is important is Ah, right. Okay. Okay, so these dashed lines are important. But what's more important is where these lines meet. Okay. So let's make these solid, and let's make them like green. How about light blue? That could work. Light blue. Okay. And then no, green. Green. Okay. And then obviously this point up here is important. Okay. And then what we do is we do the same type of intersection-based construction. Okay. And these points, these are going to be running out of colors. All right, I am going to go with blue. Okay. Light blue and light blue. Okay, and then take this point here. Okay. And then we're going to take the join HI. Okay. I think what my brain did, if you want to understand entropism, there's a great book by Kahneman and Tversky called Thinking Fast and Slow. And if you ever grade like undergraduate math homework, you notice this thing called the association heuristic, and I've just fallen victim to it here. And this is an important thing to understand. And entropism is the way humans actually think, because then so entropism is a sort of theology that Craig Cannon and I have been figuring out the last couple of years. Well, I mean, we've individually been figuring it out for a while, but lately we've started formalizing it. Oh, you know what I meant to mention? So zxq9.com, I have started writing articles here, and my Math for Programmers playlist, I'm going to basically be writing articles that mirror that playlist on here, and I'm also just going to write more stuff here. And anyway, we've started talking a bit about entropism. Yeah, the third article here is called Entropism. It's an excellent article. Yeah, so the series is called Foundations of QA, and I'll try to remember to link this. zxq9.com. And the reason I had a Substack, but I don't like Substack, and also I trust Craig a lot more than I trust Substack. Anyway, the latest one was we did a short podcast where I explained to him I'll just go, you know what? If you want to know what it's about, go read the fucking article. How about that? zxq9.com. I'll link the article. I don't remember what the article was. I do remember, but it's, you know what? It's 11 at night, and I just woke up, and I'm tired. And I apparently ran out of coffee, and so I'm kind of grumpy. Anyway, this, okay? What I'm going to show you, okay, and I'm going to highlight these points D and E, okay? And I'm going to make them pink. No, they need more contrast. Green? No. Yellow? No. Orange? These colors aren't working. Let's go with cyan, okay. I think green, we're going to have to live with green, all right? Okay. And my point is that the actual line you construct doesn't depend in any way on this point of the choice of green points. This line, which is called the polar, so the point is called the pole and the line is called the polar, is independent of the way that you choose to construct it. And in particular, you see where the polar the polar meets the circle, the polar meets the conic. Identical construction will work on hyperbolas and parabolas, I promise you. Go try it. But you see where the polar meets the conic? If I take these lines and join them back, you'll see that they end up being tangents. So I've fallen victim to the association heuristic because I haven't quite my brain detected that there was a connection and that you want some sort of Apollonius type argument for this. Let me make these. Yeah, that's a nice pink. Style. All right. So, sorry. Well, I'm not sorry about this diversion. Ooh, why does that break? Ooh, here's an interesting point, which is that in projective geometry, there's this thing called, you know how two lines in the standard blue-pilled Euclidean geometry, two lines meet, any two pairs of lines will meet unless they are parallel. Well, in projective geometry, parallel lines meet. Well, where do they meet? They meet at a so-called point at infinity. And this is, I think, the next thing I'm going to be talking. I talked about this a little bit in my abstract algebra playlist, talked about this in a couple of the podcasts with Cannon. That post I just showed you, there's links in that post to where I talked about this bit of projective geometry. But that's the next thing I'm going to be talking about in Foundations for QAnal, I think, is basic points in lines geometry. But anyway, so you notice that this sort of breaks. This breaks when these... I don't know why this is breaking. But the point is that this construction works just as well when C is on the circle, and it works just as well when C is off the circle. So, since we can draw circles and we can do this sort of points and lines stuff... Okay, the connection I was making was that you can sort of do something if you have a construction that involves tangency, you can actually get probably the exact same effect. This is the connection I was making in my head, was that if you have a construction like this, oh God, here's the problem. See this point K here? Let's delete this point K. Delete. There we go. Because, of course, Geogebra is lovely because I honestly am impressed that people could write software that is just so goddamn infuriating and also so useful. Like, it takes skill to make software that is incredibly infuriating and also incredibly useful. But anyway, this construction works just as well when C is inside the circle. By the way, the polar is the line, the pole is the point. And you can remember this is because the polar is longer and lines are longer than points. But anyway, if C is, let's find the center of the circle. If C is the center of the circle, its polar is the line at infinity, which is interesting. And then and you can see that this construction is entirely continuous, and if we kind of go across and then come back, you see the polar comes back the other side. Kind of cool. And this exact same construction also works for hyperbolas and parabolas. So let's see, what else? Oh, and if we made notice that we can never quite get to a diameter here. I can go really far away. Can never get to a diameter. I can get to the center because I chose to start with a point and constructed the line. One thing about projective geometry is it is entirely dual. So anything that you say, it is entirely symmetrical between points and lines. So anything you say about points, you can make an equivalent statement about lines. And then I'm going to walk through the algebraic formalism probably in my Math for or both in my Math for Programmers playlist and also in the Foundations of QAnal series that I'm writing on Craig's blog. Anyway, so let's you know what, you're watching this presumably because you're interested in the history of math and Greek mathematics, and so I don't think diversions are that big of an issue. Anyway, the connection I was thinking about though was I have a construction that naively involves tangency, and I can get probably the exact same in a construction that achieves the same thing by taking intersections. That was the connection that my brain pointed to, which is what we ended up doing over here, right? Okay. So the argument that Euclid is going to make, I haven't read it, but the argument that Euclid is going to make is look, we can make an isosceles triangle here. We can bisect the angle, and I don't know. How's he going to make the argument? Take an arbitrary point D on the other side of the straight line and describe the circle EFG with center C and radius CD. Bisect the straight line EG at H. EG at H, and join the straight lines CG, CH, and CE. I say that CH has been drawn perpendicular to the infinite straight line AB from the given point C, which is not on it. Since GH equals HE and HC is common, GH equals HE. Okay, yes. Yeah, so he's going to make an argument with isosceles triangles. Therefore, the two sides GH and HC equal the two sides EH and HC respectively. And the base CG equals the base CE. Therefore, the angle CHG equals the angle EHC, and they are adjacent angles. Adjacent means that you combine them and you get 180 degrees, I think. Yeah, adjacent, I think, means that together they form 180 degrees, which is a straight line. Complementary means together they form 90 degrees, I think. But when a straight line standing on a straight line makes the adjacent angles equal to one another, they're supplementary and complementary. It's something like that. I think complementary means 90 degrees, and supplementary means, I don't remember. Go look it up. Yeah, okay. He's using the argument with isosceles triangles. When a straight line standing on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is perpendicular to that on which it stands. Therefore, CH has been drawn perpendicular to the given infinite straight line AB from the given point C, which is not on it. Done. Okay, guide. Again, the double equilateral triangle construction is used, but this time double equilateral triangle. I don't know. But this time the preparation of the starting line EG is different. The point D is taken on the other side of the line AB to ensure that ensure that the circle meets the line AB in at least 2 points, E and G. If D is taken on the line AB, it might be taken at H, and the resulting circle would touch the line only at H. And if D is taken on the same side of AB, then the circle would miss the line entirely. Euclid does not precede this proposition with propositions investigating how lines meet circles. He's much more careful in Book 3 on circles, in which the first dozen or so propositions lay foundations. For instance, Proposition 3.10 states that a circle does not cut a circle at any more than 2 points. Even so, some propositions are missing. One is needed for this proposition to justify the existence of the 2 points C and E, which I think are the existence of C and E. I think he means E and G. G and E, where the line AB meets the center. Yeah, okay. A circle whose center is on right, something like that. Such a proposition would state a circle whose center is on one side of a line and whose circumference lies at a point on the other side of the line, meets the line at 2 points, Incidentally, Proclus explains in his commentary on Book 1 that the problem of constructing the perpendicular was invested by fucking Greeks. Oenopides of Chios, who lived sometime in the middle of the 5th century BCE, a century and a half before Euclid. Use of Proposition 12. The construction of this proposition is not used in Book 1, but is used on occasion in the remaining geometric books, namely Books 2 through 4, 6, and 11 through 13. All right. Whew. Got through the video. What should be the thumbnail? I think the Euclid construction will be the thumbnail. I'll make it a little bit prettier. All right. Thank you for watching. If you watched all the way through, I will see you in the next video. Go check out the articles that I talked about. Bye.